this lecture, we will discuss about diagonalization of a matrix and one problem based on diagonalization and algebraic and geometric multiplicity. If a matrix A is diagonalizable, if there exists a invertible matrix P such that P inverse A into P is called as D. Here where D is called as diagonal matrix. So in this, here a matrix A is diagonalizable if there exists a invertible matrix P. See, P inverse nothing but the invertible matrix of P. So such that this condition will be satisfied. P inverse A into P is equal to D. Here D is nothing but diagonal matrix, and in this matrix P is called as model matrix, and this model matrix is formed by eigenvectors, and the diagonal matrix D is called as spectral matrix. So the diagonal matrix is also called as spectral matrix. So here we write the P as eigenvector of first eigenvalue, eigenvector of second eigenvalue, and eigenvector of third eigenvalue. We write in a matrix that is called model matrix, which is denoted by P, and we write the diagonal matrix D as lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. So here lambda 1, lambda 2 and lambda 3 are eigenvalues. So we write in this matrix that is called as D, first eigenvalue, we write we write the eigenvalues in a diagonal and the remaining elements are 0. Here it is a model matrix P, and here we denote the eigenvectors of these eigenvalues. And note, the diagonal elements are the eigenvalues of A. So in this diagonal matrix, the diagonal elements are the eigenvalues of the matrix A. The matrix A is diagonalizable if algebraic multiplicity is equal to geometric multiplicity. So we have discussed what is algebraic and what is geometric multiplicity in previous video. If algebraic multiplicity is equal to geometric multiplicity, then we can tell that the matrix A is diagonalizable. And if A is symmetric, matrix, then it satisfies this formula as P transpose into A into P, that equals to diagonal matrix D. So if A is a symmetric matrix, then P transpose into A into matrix P, that is equals to diagonal matrix D. And if A is diagonalizable, then A power n equals to P into D power n into P inverse. So whenever we want to find out the A power n, here we have seen that matrix A is diagonalizable if algebraic multiplicity equals to geometric multiplicity. After this condition, we can tell that matrix A is diagonalizable. So when it comes to the diagonalizable, then if they ask like a power 3 or a power 8, so directly we can use the formula as p into d power n into p inverse. So if they ask if n is equals to 3, then substitute this 3 in this equation, you get it as a power 3 p into d power 3 p inverse. So when you solve this equation, you get the value of a power 3. We go with one problem. Is the matrix is diagonalizable? Check whether the given matrix is diagonalizable or not. We know that the condition for diagonalizable is algebraic multiplicity should be equal to geometric multiplicity. If algebraic multiplicity equals to geometric multiplicity, then we can tell that the given matrix is diagonalizable. If not, then it is not diagonalizable. Here the matrix comes as 3, 10, 5, minus 2, minus 3, minus 4, 3, 5, 7. So first write the matrix. Let A is equals to 3, 10, 5, minus 2, minus 3, minus 4, 3, 5, 7. The characteristic equation of A is determinant of A minus lambda I is equal to 0. So just subtract the lambda from the diagonal elements and we get it as 3 minus lambda, 10, 5, minus 2, minus 3, minus lambda, minus 4, 3, 5, 7 minus lambda, and that equals to 0. So when we solve this, we get the cubic equation as this is a order of 3. Then we get the cubic equation in the form of lambda cube minus s1 lambda square plus s2 lambda minus s3 equals to 0. So here s1 nothing but trace of A. Trace of A is nothing but sum of the diagonal elements. 3 plus of minus 3 plus 7. That is 3 minus 3 plus 7, that equals to 7. And s2 comes as minus. Here take the first diagonal element, delete this row and column and find the minor of remaining elements. Similarly, take second element of diagonal as minus 3 and delete this row and column. Write that find the minor of remaining elements. As if we write here minus 3, minus 4, 5, 7. This is a minor of 3 and 3, 5, 3, 7. This is a minor of minus 3. 3, 10, minus 2, minus 3. This is a minor of 7. Then when we solve, minus 3 into 7 is minus 21. Minus 4 into 5 is minus 20. So when we subtract it, it becomes minus of minus 20, that is plus 20. Then here 21 plus 21 minus 15 minus 9 plus 20. So here we get it as 16. And S3 nothing but a determinant of the matrix A. So 3 into the minor minus 21 plus 20 and minus 10 of minus 14 plus 12 plus 5 of minus 10 plus 9. Here 3 into minor of these elements, we get it as minus 21 into minus 20. So 3 into minus 21 into plus 20, minus 21 plus 20, and here minus 10 into minus 14 plus 12. So minus 10 into minus 14 plus 12, and here 5 into minus 10 plus 9. Then here we get it as 3 into minus 1, minus 10 of minus 2 plus 5 of minus 1, and that equals to 12. So here the equation comes as lambda cube minus 7 lambda square plus 16 lambda minus 12 equals to 0. This is the equation we got. Here we got the equation as lambda cube minus 7 lambda square plus 16 lambda minus 12 equals to 0. So solve this equation and get the values of lambda. For that we use the calci here. First on the calci. then click on mode setup, then click on 5 for equations, click on 4 for cubic equation. Now enter the coefficients of lambda cube, lambda square, lambda and constant. Lambda cube coefficient comes as 1 equals to lambda square coefficient minus 7 equals to lambda coefficient 16 equals to, and constant comes as minus 12. So that equals to, we get the eigenvalues as 3, 2. Eigenvalues as 3 and 2. So when again we click on equals to, it comes back to the equation. So here nothing but we need to get a 3 solutions for this equation, as this is a cubic equation. So we got only 2 values as 3 and 2. So we had to take the last value which we got, we had to take it as a repeated one. So here the repeated value is 2 and the eigenvalues are 3, 2, 2. So first write the matrix 3 minus lambda, 10, 5, minus 2, minus 3 minus lambda, minus 4, 3, 5, 7 minus lambda. This is a characteristic equation into variable matrix x, y, z, and that equals to 0, 0, 0. So let this be as equation number 1. Now here case 1. Here we need to check whether the given matrix is diagonalizable or not. Just put lambda equals to 2. Here no need of taking lambda is equals to 3, as at last we need to find the arithmetic algebraic multiplicity and geometric multiplicity. So for that I am taking the value as only lambda 2. So put lambda equals to 2 in equation 1. So here when we keep 3 minus 2 is 1, 10, 5, minus 2, minus 3 minus 2 is minus 5, and minus 4, 3, 5, 7 minus 2 is 5 into variable matrix x, y, z, and that equals to constant matrix 0, 0, 0. So from this write the equations. So the equations comes as x plus 10y plus 5z equals to 0, equation 1. From this minus 2x minus 5y minus 4z equals to 0, equation 2. And from this third row, 3x plus 5y plus 5z, that equals to 0. This is equation number 3. So I am taking the equations 1 and 2 and I am solving them. Equation 1 and 2, x, y, z. So from this equation y and z, first write the coefficients of y as 10 and minus 5. Next write the coefficients of z as 5 and minus 4. Next write the coefficients of x 1 and minus 2. Then at last write the again coefficients of y as 10 and minus 5. So when we solve this, 10 into minus 4 is minus 40 and minus into minus is plus 25. That equals to y by minus 10 and minus of minus 4, that is plus 4, and that equals to z by minus 1 into minus 5 minus 5, and 10 into minus 2 is minus 20, and that is minus of minus 20 is plus 20. So here x by minus 15, that equals to y by minus 6, z by 15. So that equals to x by minus 5, y by minus 2, and z by 5. So the vector we got it as x1 equals to minus 5, minus 2 and 5. So this is the eigenvector, is only one vector for eigenvalue lambda equals to 2. So as we have seen, the lambda is 2, that is which is repeated 2 times. So we need to get the two eigenvectors for 2. But here we got only one eigenvector for lambda equals to 2. Here we need to check whether this is diagonalizable or not. We know that algebraic multiplicity of 2. So for eigenvalue 2 is 2. So here 2 nothing but, as the lambda equals to 2 and this eigenvalue is repeated for twice, it is repeated for 2 times, so that is what we are taking it as 2. So algebraic multiplicity of eigenvalue 2 is 2. Then geometric multiplicity of 2 is 1. So here the 1 comes as because for eigenvalue 2 we got only one vector as -5, -2, 5. So there is only one vector for eigenvalue 2. Then we are taking that geometric multiplicity of 2 as 1. Or you can solve this geometric multiplicity as n minus r, where n is nothing but order of the matrix, or you can call it as the number of variables included in the matrix. Here we know the variables are x, y, z, so n is equals to 3. So you find the rank and you will get it as r equals to 2. Then when you do n minus r, that equals to 3 minus 2, then n minus r you will get it as 1. This gives the geometric multiplicity. So you can, if you find in this way, you need to find the rank of the matrix and you need then you will get the then you have to solve n minus r, you will get the value as 1, and that is the geometric multiplicity. So it is very hard at the time of examination, as you need to save the time. So for that we go with this method, as geometric multiplicity of 2 is, so as we got only one vector for eigenvalue 2 which is repeated. So therefore here we have seen algebraic multiplicity is not equals to geometric multiplicity. So here we can tell that the matrix A is not diagonalizable, since algebraic multiplicity is not equals to geometric multiplicity. Thank you.